dear students, glad to meet you again in this session. In this session 2.10, we are going to discuss energies of orbitals from chapter 2, structure of atom in grade 11. Before getting into today's concept, let us recall all the topics that we have discussed in the previous sessions. In session 2.1, we have discussed subatomic particles and its classifications. In session 2.2, we have discussed the atomic model, that is J.J. Thomson atomic model, Rutherford atomic model and its drawbacks. In session 2.3, we have discussed the dual nature of electromagnetic radiation. In session 2.4, we have seen the continuous spectrum, emission spectrum, absorption spectrum, atomic spectrum, and line spectrum of hydrogen. In session 2.5, we have discussed the postulates and explanation of Bohr's atomic model for hydrogen atom, line spectrum of hydrogen atom, and limitations of Bohr's model. In session 2.6, we have discussed the two developments, that is de Broglie's relationship and Heisenberg's uncertainty principle that leads towards quantum mechanical model of atom. In session 2.7, we have discussed quantum mechanical model of an atom. In that, we have discussed Schrödinger wave equation, significance of psi, the wave function. In session 2.8, we have discussed orbital and quantum numbers. We have discussed 4 quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and electron spin quantum number. In session 2.9, we have discussed the shapes of s orbitals, p orbitals, d orbitals, and f orbitals. Learning outcomes. Students, at the end of this session, you will be able to explain the increasing order of energies in hydrogen atom, describe the energy level diagram of hydrogen, enumerate the effect of nuclear charge, compute the values of order of energies in various orbitals using n plus L rule, and describe the energy level diagram of multi-electron atoms. Before getting into today's concept, let's recall Bohr's model of hydrogen. In Bohr's model of hydrogen, the energy of the electron revolving in the nth orbit is given by the expression E suffix n is equal to minus k square into 2 pi square m e power 4 into z square upon n square into h square. Substituting the values of m, e, h, pi, k, and z in the above expression, we get the energy of the electron E suffix n is equal to minus 2.18 into 10 to the power of minus 18 upon n square in terms of joules per atoms. If we express this unit in terms of electron volt per atom, then En is equal to minus 13.6 upon n square. So the energy of the electron in the nth orbit is given by the expression E suffix n is equal to minus 13.6 upon n square in terms of electron volt per atom. If we want to express in terms of kilojoules per mole, then the value of En is equal to minus 1312.8 upon n square. From this expression, we come to know that the energy of the electron in hydrogen atom depends upon the value of n, that is the principal quantum number. If we substitute n equal to 1 in this expression, then En is equal to minus 13.6 upon 1, right? So the value of En for the first shell, that is the K shell, is minus 13.6 electron volt. If we substitute the value of n equal to 2 in this expression, then we get En is equal to minus 13.6 upon 2 into 2, 4, right? So when we divide minus 13.6 upon 4, we get the value of En as minus 3.40 electron volt in the L shell. If we substitute the value of n equal to 3 here, then we get the value of En as a minus 1.5 electron volt in M shell. When we note down the values of energy in these shells, we come to know that as the value of n increases, the energy of the orbital also increases. Since it is a negative value, minus 13.16 is lesser than minus 3.40, right? Which is lesser than minus 1.5 electron volt. So as the value of n increases, the value of the energy of the orbital also increases. In hydrogen atom, there is only one electron, and this electron will be present in the 1s orbital that has the lowest energy. So this state is called ground state. When this electron gains more energy, it jumps to the higher orbital such as 2s, 2p or 3s, 3p, 3d and so on. These states are called excited states. The energy of the electron present in 1s orbital, which is in the K shell, will be lesser than the electron present in 2s or 2p orbital, which is present in the L shell. Though the shape of 2s orbital is different from that of 2p orbital, the electron has the same energy whether it is in the 2s orbital or 2p orbital. The orbitals having the same energy are called degenerate. For such one electron system, the various energies of the orbital will be in the following order. So the increasing order of energies of electrons present in various suborbitals present in hydrogen atom will be in the following order. So the energy of the 1s orbital present in the K shell is lesser than the energy of the electrons present in the L shell, which is less than the energy of the electrons present in the M shell. So 1s will be less than 2s, which is equal to 2p, which is less than 3s, which is equal to 3p and 3d, which is less than 4s, which is equal to 4p, 4d and 4f, which is less than 5s, which is equal to 5p, which is equal to 5d and 5f. And this energy of the electron will be less than the energy of the electron present in 6s, which is equal to 6p, which is equal to 6d and 6f. And the energy of the electron will be less than the energy of the electron present in 7s. Now let's see the energy level diagram of hydrogen atom. An energy level diagram is nothing but a diagrammatic representation of relative energies of various orbitals in an atom. As we have discussed already, for a single electron system such as hydrogen or hydrogen-like atoms, all the orbitals in a particular energy level, that is in a particular principal quantum number or in a particular shell, will have the same energy. For example, in a single electron system like hydrogen or hydrogen-like species, the energy of the electron, whether it is present in 6s orbital or 6p suborbital or 6d suborbital or 6f suborbital, will have the same energy. Likewise, whether the electron present in 4s orbital or 4p orbital, 4d orbital and 4f orbital will have the same energy. So for hydrogen or hydrogen-like species, the principal quantum number is very important because it determines the energy of the orbitals. As we have discussed earlier, in a single electron system, since there is only one electron, the energy of the electron depends only on the principal quantum number n. But here in multi-electron atoms, the energy of the electron depends not only on the nuclear charge, that is the force of attraction between the positive charge nucleus and the electron, but also the repulsion between the electrons present in the atom. For a given principal quantum number n, the energies of the suborbital s, p, d, f in a multi-electron system differ from each other because of the mutual repulsion of the electrons. And as we have discussed earlier, due to the presence of the electrons present in the inner shell, the electrons present in the outer shell will not experience the full positive charge of the nucleus. The shielding of the outer electrons from the nucleus by the inner electron reduces the effect of positive charge of the nucleus upon the outer electrons. So the net positive charge experienced by the electron from the nucleus is called the effective nuclear charge. Even though there is a shielding effect which reduces the effect of full positive charge of the nucleus upon the electrons present in the outer shell, The attractive force experienced by the outer shell electrons increases with increase in the nuclear charge. Therefore, the effective nuclear charge of oxygen is greater than the effective nuclear charge of the carbon. The stability of the electrons in a multi-electron atom is because of the total attractive interaction is greater than the total repulsive interaction. The attractive interaction of electron increases with increase in the positive charge on the nucleus. Shielding effect of various suborbitals. The effective nuclear charge depends on the shape of the orbital. It increases with increase in the azimuthal quantum number. We know that s orbitals are spherical in shape. The spherical shape s suborbitals have maximum space for the electrons to move around it. So it have maximum shielding effect when compared to other suborbitals like p, d and f suborbitals. So the shielding effect of various suborbitals is in the following order. The shielding effect of s orbital will be greater than the shielding effect of p orbital, which is greater than the shielding effect of d orbital, which is greater than the shielding effect of f orbital. Increasing order of energy in a multi-electron atom. Since the electron in various suborbitals have experienced different effective nuclear charge in the case of a multi-electron system, even though all these suborbitals present in the same shell, it leads to the splitting of energy within the same shell. The energy of various suborbitals will be in the following order. That is, the energy of s suborbital is lesser than the energy of p suborbital, which is less than the energy of d suborbital, which is less than the energy of f suborbital. That is, the energy of f orbital will be higher when compared to the energy of the s orbital, even though it is present in the same shell. Hence, within the same energy level, that is, if we consider m shell, the energy of s orbital will be less than the energy of p orbital, which is less than the energy of d orbital. We know that the electrons in the suborbital, which is closer to the nucleus, will experience a high effective nuclear charge. If there is a high effective nuclear charge, then the stability of the electron present in the subshell will be greater. Greater the stability, lesser the energy. Thus, the energy of the electron present in 1s orbital, which is very near to the nucleus, experience a high effective nuclear charge and it has a very low energy level. So we call it as a ground state level. This shows greater the effective nuclear charge, lesser the energy. For a multi-electron system, the Schrödinger wave equation is quite complex. In a multi-electron system, both the attractive interaction and the repulsive interaction. Attractive interaction means the attraction between the positive nuclear charge and the negative electrons, and the repulsive interaction, that is the repulsion between the two electrons, depends upon the shell, that is the principal quantum number n, and the shape of the orbital in which the electron is present. So for a multi-electron system, the relative order of energies of various orbitals is given by n plus L rule. We know that n is the principal quantum number and L is the azimuthal quantum number. Now let us see how to calculate the n plus L value. Order of energy in a multiple electron atom depends upon n plus L rule. We know that n is the principal quantum number and L is the azimuthal quantum number. For 1s orbital, since it is present in the first shell, the value of principal quantum number n equal to 1. So n equal to 1. S means it represents the azimuthal quantum number value L equal to 0. So for this 1s orbital, what is the n plus L value? It is 1 plus 0, that is 1. If we calculate for 2s orbital, the value of n is 2 and the value of L equal to 0, since it is a s suborbital. So what is the value of n plus L? The value of n plus L is 2 plus 0, that is 2. Coming to 2p orbital, the value of n equal to 2 since it is present in the second shell, L shell, and the value of L equal to 1 since it is a p orbital. So what is the value of n plus L for this 2p orbital? 2 plus 1, that is 3. Coming to 3s orbital, the value of n equal to 3 and the value of L equal to 0 since it is a s orbital. So what is the value of n plus L? The value of n plus L is 3 plus 0, that is 3. So when you notice these two values, it has the n plus L value 3 for both 2p orbital and 3s orbital. For such cases which have the same n plus L value, the lower the value of n will have the lower energy. Likewise, when we calculate the n plus L value for 3p orbital and 4s orbital, we have the same n plus L value, that is 4, right? So among these two orbitals, which will have the lower energy, the lower the value of n will have the lower energy. So 3p orbital will have the lower energy when compared to 4s orbital. If we calculate the n plus L value for 3d orbital, what is the value of n? N is equal to 3. And what is the value of L for d orbital? 2. So 3 plus 2, 5, right? Even though 3d orbital is present in the M shell, it has the higher value of energy when compared to 4s orbital, which is present in the N shell, because the n plus value is 4 for 4s orbital and it is 5 for 3d orbital. So according to n plus L rule, the increasing order of energies of various orbital is in the following order. Now let us see this order with the help of this energy level diagram of a multi-electron atom. The energy of electron in 1s orbital is less than the energy of the electron present in 2s orbital, which is less than the energy of electron present in 2p orbitals, which is less than 3s orbital, which is less than 3p orbital, which is less than 4s orbital, which is less than 3d orbital, which is less than 4p orbital, which is less than 5s orbital, which is less than 4d orbital, which is less than 5p orbital, which is less than 6s orbital, which is less than 4f orbital, which is less than 5d orbital, which is less than 6p orbital, which is less than 7s orbital, which is less than 6d orbitals. If you look at the energy level diagram of one electron atom and multi-electron atom, we could see the different subshells present in a particular shell. That is, if we take the L shell, the 2s orbital and 2p orbital suborbitals have different energies in the case of multi-electron atom, not in the case of one electron atom. In one electron atom, these suborbitals have the same energy. The energy of the same atomic orbital decreases with increase in the atomic number. The energy of 2s orbital of hydrogen is greater than the energy of the 2s orbital of lithium, which is greater than that of sodium, which is greater than that of potassium. Students, now let's recall all the topics that we have discussed in this session. We have discussed the increasing order of energies in hydrogen atom, energy level diagram of hydrogen atom, effect of nuclear charge, the values of orders of energies in various orbitals using n plus L rule, and finally we have discussed the energy level diagram of multi-electron atom. Hope this session was very useful to you. Meet you in the next session. Have a nice day. Thank you.